Sample 7-2 up the hill is on page 283 in your textbook. I love this problem because it puts together almost everything we've done over the last couple of units. We need to push a box of supplies from your car to a campsite 6 meters up a 5-degree incline. Now note they give you the weight of the box of supplies. So if you want the mass, you have to divide out the 9.8 meters per second squared. You exert a force of 85 newtons parallel to the incline, and a 56 Newton kinetic friction force is exerted on the box by the ground. We're going to calculate how much work you do on the box, how much work gravity does on the box, and how much work friction done on the box. And then finally, we'll calculate the net work done on the box by adding up all those numbers. So let's start with a free body diagram just because hopefully it's useful and natural to you at this point. There's my gravity, there's my normal force. This is my applied force up the hill, okay? So no angle with the slant. And there is my frictional force. And you'll notice they did us the favor of actually giving us the frictional force. We don't have to calculate the normal force and then mu k times the normal force. They kind of did that for us. When we put it all together, you will have to do all of that, but let's make it easy. Okay, so we've got the weight of this crate, is 225 newtons. And the type A part of me wants to find the mass and just write it down in case I need it. We know it's going to move a distance of 6 meters, and I probably should have added that to my drawing here. This is the direction of displacement up the ramp, okay? And the amount is 6 meters. Okay, the applied force is given as 85 newtons, and we're told that friction is going to pull us back with 56 newtons. Okay, so work done by the applied force, and we can use subscripts in work just like we did for force, and in fact, I suggest that you do. Okay, it's equal to the applied force times the distance times cosine theta. Now, in the incline plane problems, you got to keep your theta straight because the ramp is tilted at a 5-degree angle, but we also have a theta in our work problem. It's not the same theta, so let's be careful, and I'll try to describe exactly why I put the numbers where I do. Okay, the applied force is easy, 85 newtons. It moves 6 meters. Now, what's the angle between the applied force and the displacement? If you look up at our free body diagram, the applied force and the displacement are going in exactly the same direction. That angle is 0, so the cosine is 1. Positive 1, by the way. So we get an answer of 510 joules for the applied force, all right? Now I'm going to do part C first. It doesn't matter, but I have a reason. Let's do the force done by friction. The work done by friction. That's Fk times d times cosine of theta. Remember, that's the angle between friction and the displacement. So the force due to friction is 56 newtons. They were nice, and we didn't have to calculate it. The distance is always the same, right? There's only one thing moving, and it's only moving one distance. So in these problems, that's the easy part, so don't make it difficult. Now, for the angle. Friction is acting down the ramp. The displacement is up the ramp. That's a 180-degree angle. And the cosine of 180 degrees is -1. So that goes there in my FT cosine theta formula. So now I'm going to get a -336 joules. Okay, now let's deal with gravity. Okay, so that's the force due to gravity times the displacement times the cosine of theta. Now, this is the tricky part, but if you do this right, okay, remember that the force due to gravity is just mg sine theta, but instead of getting confused with the theta in the work equation, let's just do sine 5 degrees, just like that, and just not even put the angle in there, okay? Now, we've got our 6 meters as our distance, and then now cosine theta, this is the angle between the gravitational force and the displacement. Now, the gravity is not actually pulling the box straight down, it's pulling it down the ramp. So the angle for the gravitational force, or the component of the gravitational force, is 180. So we put a -1 there. There's a couple different ways to break the gravity force into components in the work problem. I think this is the easiest way. If you look at your picture, it should be clear that gravity is pulling the box down the ramp. There are no forces that are, well, never mind. So the answer you get for this one here is -117 joules. Now you'll notice that the normal force, we didn't do anything with the normal force. The normal force isn't doing any work on this box because the normal force is perpendicular to the incline and the displacement is parallel to the incline. So in this problem, the only reason for calculating the normal force would be to multiply that by mu k and find the frictional force, but we didn't even have to do that. So the normal force didn't really come out to play in this problem. That's okay. So we found the work done by all of the forces that are doing work, and this is how I'm going to ask you the question on the exam. I'm going to say, draw a free body diagram. Which of those forces are doing work? And your answer is the applied force, friction, and gravity. Then I'm going to say, how much work is done? And you calculate like this. Now we say the net work. Right, the net work done on this box is the work done by the applied force plus the work done by gravity plus the work done by friction. Now resist the urge to positive and negative here. Just the net work is the sum of all of them. We've got our negative signs here, so let's just use them at this point. 510 joules minus 117 joules minus 336 joules means there's a net work of 57 joules done on this box. And next section, we'll talk about what that does to the box. In fact, we can increase its speed by applying a network. We'll get there next topic, but make sure that this problem makes sense to you, because I haven't even started to think about your test yet, but I can guarantee that something like this or very much like this will appear on your Unit 4 exam. So let me know if you have any questions.